A 2-3 kilogram spare tire usually sits quietly in a car's trunk, motionless and seemingly harmless. It does not move, burn fuel, or make noise. Yet herein lies the paradox. Its very passive existence pulls the entire world onto a massive trajectory of energy loss. Imagine this: if 1 billion cars each carry an unnecessary 23 kilograms. Humanity is transporting 23 billion kilograms of excess mass. That is an artificial mountain equivalent to 300 Eiffel Towers, rolling across every road, climate, and continent every single day. The harsh truth is, simple energy does not care whether an object is useful or not. In dynamics, whether it is a spare tire or a nameless rock, mass always carries an energy cost. Engineers have therefore begun to view the spare tire not as a symbol of traditional safety, but as an entropy leak, an object that increases system complexity, reduces efficiency, and quietly demands that the planet pay in CO2 emissions. Day after day. From this contradiction, a philosophical battle emerged within the automotive industry. Could removing 20 kilograms help save the planet? And if so, what physical laws are forcing us to abandon a century-old tradition? In vehicle motion, few forces appear more innocent than rolling resistance. It is weaker than aerodynamic drag and less complex than engine friction. Yet it represents one of the most unavoidable sources of energy loss. As a wheel rolls, the contact patch between tire and road undergoes continuous cyclic deformation, compression followed by recovery. The heavier the vehicle, the greater this deformation. This deformation is not perfectly elastic. A portion of mechanical energy is converted into heat through internal friction within the rubber, a phenomenon known as hysteresis loss. This is microscopic entropy in action energy. Once organized as forward motion is dispersed into useless molecular vibrations. As a result, adding just 20-25 kilograms increases rolling resistance enough to waste millions of liters of fuel when scaled across billions of vehicles. More critically, rolling resistance depends not only on total mass but also on mass distribution. A spare tire positioned at the rear shifts load balance, forcing the suspension to work harder and creating additional compression extension cycles, each one another small but continuous drain of energy. From a kinetic energy perspective, a vehicle must supply energy to accelerate every object it carries. A 20 kilogram mass accelerating from 0 to 100 kilometers per hour absorbs approximately 77 kilojoules of kinetic energy, roughly the amount needed to heat a cup of cold water to near boiling. Every time you accelerate, the spare tire consumes fuel simply to remain motionless. The emergence of run-flat tires marked a technical turning point, where polymer physics replaced the century-old philosophy of relying on air pressure. In conventional tires, compressed air bears most of the load. When pressure is lost, the structure collapses, forcing the use of a spare tire. Run-flat tires solve this problem by reinforcing the sidewalls. At the material level, they are dense, cross-linked polymer networks designed to sustain compressive loads independently of air pressure. These polymer chains, typically butyl, rubber, or synthetic elastomers, are reinforced with aramid fibers or Kevlar, preserving elasticity while resisting deformation. When a run-flat tire loses pressure, the entire load transfers to the sidewall rather than the air chamber. This creates a thermal challenge. Continuous sidewall deformation generates heat rapidly. To address this, run-flat tires incorporate passive thermal management strategies using low-conductivity material layers and microscopic cooling channels. This design mirrors principles found in biological bone structures, optimizing load paths and dispersing stress efficiently. By transforming the sidewall into an intelligent load-bearing column, engineers eliminated the need for a fifth wheel. Once again, 20 kilograms were saved without sacrificing safety. Modern tire repair kits rely on a subtle chemical mechanism, polymerization, the process by which small molecules link together into larger networks. When activated, The sealant typically contains latex or styrene butadiene polymers. When injected into a punctured tire and exposed to air, polymerization begins almost instantly. Air acts as a microscopic catalyst, generating free radicals that trigger polymer bonding. At the same time, centrifugal force pushes the liquid sealant outward along the inner tire wall, concentrating it at the leak site. The process closely resembles blood clotting in biological systems, an automatic repair response, but executed with synthetic materials. Within seconds, a dense polymer network forms, sealing the puncture. Internal pressure is restored almost immediately, allowing the vehicle to continue driving for 50 to 100 kilometers without damaging the rim or suspension. Remarkably, this mechanism requires only a few hundred grams of material, less than 1/100th the mass of a traditional spare tire. This is where chemistry outperforms mechanics instead of carrying a bulky object. The vehicle carries repair capability, compressed into a chemical reaction. In the era of electrification, interior vehicle space has become as valuable as fuel itself. Energy is no longer evaluated by mass alone, but by energy density. A spare tire occupies 25 to 40 liters of volume, enough space to house 6 to 7 lithium-ion pouch battery modules. Lithium-ion batteries offer an energy density of approximately 250-300 watt-hours per kilogram by weight and 600-700 watt-hours per liter by volume, making them the white gold of electric vehicles. Every liter allocated to batteries extends driving range, reduces charging frequency, and lowers total life cycle CO2 emissions. Skateboard-style vehicle platforms, the foundation of modern electric cars, depend on near-perfect spatial optimization. Flat battery modules beneath the floor demand that every cubic centimeter be justified. A large cavity reserved solely for a spare tire becomes an unacceptable static waste of space. From a systems architecture perspective, removing the spare tire enables a complete vehicle redesign, reinforced body structures, a lower center of gravity, improved aerodynamics. All this change comes from eliminating 20 kilograms and a few dozen liters of volume, but in systems science, that is the difference between an efficient design and an obsolete one. 20 kilograms may seem insignificant, but in a world of 8 billion people, they could save an entire planet.